Good evening. I'm Mr. Ish. We're looking at a single question here, an intimidating question slightly with regards to a solid of revolution or a solid of rotation. Thank you for joining me for this video. Our function is y equals cosine x, or f of x equals cosine x within the interval pi over 4, including pi over 4 to 3 pi over 4, and including that basically 45 degrees to 135 degrees with a rotation around the y-axis. This is an excellent example in terms of using the cylindrical shell technique. If you graph it out, you'll be able to see exactly what we're talking about. Here's my pi over 2. Cosine x has a y-intercept at 0, 1. Not a difficult graph. When you take it down, it looks something like that. If this right here is my pi over 4, which is 45, and this right here is 3 pi over 4, which is 135, you're looking at this area region between the curves, and then this area right here, region between the curves. What you end up seeing is that x-intercept of pi over 2, right, pi over 2 comma 0 ends up splitting this area between the curves into two parts. One is above the x-axis and the other one is below the x-axis. One is below the curve, one is above the curve. You see that split over there, and that split creates a little bit of an issue, especially when you're looking at a rotation on the y-axis. It would be very difficult to generate what this solid would look like, but we can probably try to attempt and draw it out. It would look something like this. This right here is on one side, and then when you mirror it on the other side, it would look something like that with regards to what appears on the other side. Of course, we're doing a very rough sketch over here, and we can just polish it up a bit. You'll have a solid which would look something like this. All of this right here would be dotted inside. I won't attempt to draw it. This right here would be mirrored by exactly that right there, and then you'd have a representation here going here and coming here, and then one right here, and then coming right here in the background. That would be your solid. It would be a very difficult solid to very well comprehend. Open here from the top, very large amount, and open here, very large amount on the bottom, and slowly funneling its way through. But that right there is a solid of revolution that would develop with this specific function from this pi over 4 to 3 pi over 4. The challenge here is to actually determine the volume of the solid I have drawn and which I have now erased. You have to develop here two integrals here, and I'll show you and I'll tell you why. If you're looking at everything right over here, and let's only draw part of it like this. This is what you're looking at, a Riemann rectangle here and a Riemann rectangle here. Everything here with regards parallel to your line of rotation, which is your y-axis, and then looking across perpendicular. When you're looking here in terms of these looking across, you're looking at an x dimension. Your radius here is going to be x, your circumference will be 2 pi x. But the height here is a problem because your height differs based on what part of the interval you are. From this pi over 4 up to pi over 2, you have a different value for your height, and from pi over 2 to 3 pi over 4, you have a different value. So your height here is cosine x, but when you're looking from pi over 4 to pi over 2. But your height here, and remember the height here is yt minus yb, top boundary curve minus lower boundary curve. But then from pi over 2 to 3 pi over 4, your top boundary curve is your x-axis, which is 0, and your lower boundary curve is cosine x, which is minus cosine x right here. And then you're looking here from pi over 2 to 3 pi over 4, and you can see this 0 minus cosine x is just minus cosine x. So you can develop the integral based on exactly what you see here. Your integral will be exactly how I will write it. From the first interval, pi over 4 to pi over 2, you have x cosine x. Remember, it's always circumference times height times your thickness. Here's my thickness, plus. Now we have this other component. I'm always isolating 2 pi from the circumference and pushing it out because I'm used to doing that. And then here you're looking from pi over 2 to 3 pi over 4. You still have this x, and then you have a minus cosine x, and then you have a dx, and that right there is our integral form. But to make your integral form look easier, get rid of this minus sign, same minus sign which is generated here, and then change this into a minus. There's nothing wrong with you doing that. Bring the minus from here to here. Now we have to actually integrate this, and we need space for that, and you see all of this here before you. Everything here looks right to me, so I'm removing it. To integrate this x cosine x, it's easy. You just have to use integrating by parts. U is equal to x, du is equal to dx, v is equal to integral of what remains, cosine x, right? dx, which is sine x. and then uv minus integral v du will give you what you need to put over there. U will be x, v will be sine x, minus integral v du is sine x dx. Alright, see, dx. When you do all of this, you get x sine x. You'll have here a minus cosine x antiderivative, which will hit with this minus, and you get a positive cosine x. That will generate from all of this. The only reason why you don't have to change the intervals when you're doing here, this is not a polynomial substitution technique, it's an integrating by parts technique. Your intervals stay the same. Think about it. You have a x1, x2, you'll have a u1, u2. If u is always equal to x, then u1 equal to x1 and u2 is equal to x2. So the intervals never change. So we have this as our antiderivative. Let's bring it in over here. We'll have 2 pi, and then we'll have all of this x sine x plus cosine x. This right here is from the upper interval pi over 2 and lower interval pi over 4. And then we have this minus. Then we have exactly the same antiderivative coming from there because the integrand was the same, only the intervals changed. We'll here again have x sine x plus cosine x, and then now here we have 3 pi over 4 and pi over 2. So I promise you this is an interesting question and it's turning out to be one. Now we have a messy part here. We have to put the upper limit pi over 2 in places of x and pi over 4 in places of x and the difference of the two. Here we have to do 3 pi over 4 in the places of x and then pi over 2 and then the difference of the two. And we'll be doing a little bit of work over here to get to our final answer. In this entire expression we'll put pi over 2 first. X pi over 2, well, you just have a pi over 2. And then sine pi over 2 is just a 1, we don't have to write that. Plus cosine pi over 2 is a 0, we don't have to write that. Placing pi over 2 in places of all of these x's has just generated me this pi over 2. Now we'll put pi over 4 in here. In places of this, we have a pi over 4 in this x. Sine pi over 4 is a 1 over root 2 plus cosine pi over 4 is a 1 over root 2. This right here is the result of definite integration with the 90 and the 45 coming into play. Now we have this, and let's work on this side. 3 pi over 4 in places of x first. 3 pi over 4, sine of 3 pi over 4 is a 1 over root 2, right? Plus cosine of 3 pi over 4 is a minus 1 over root 2 because it's a second quadrant cosine angle. Alright, this right here is the result of putting the upper limit in. Now we'll do with the pi over 2. Pi over 2 come in place of x is just a pi over 2. Sine of pi over 2 is a 1, cosine of pi over 2 is a 0, it doesn't matter, and that's all we get from there. Let's bring everything together here. We have a pi over 2 minus pi over 4 root 2 minus 1 over root 2 minus 2 pi, and let's work here. We have a 3 pi over 4 root 2 minus 1 over root 2 minus pi over 2. What we can do over here is basically bring everything together and isolate the 2 pi. I isolate the 2 pi and I'll open all of this up, keeping in mind that I've isolated the 2 pi from here. I have a pi over 2 minus pi over 4 root 2 minus 1 over root 2. This minus with that is a minus 3 pi over 4 root 2. At the end I want to present my answer in decimals. This minus with this minus becomes a plus 1 over root 2. This minus with this minus becomes a plus pi over 2. Combine the like terms. We have a 2 pi sitting here. Pi over 2 plus pi over 2 is a single pi. Minus 1 over root 2, positive 1 over root 2 cancel out, which is good. Minus pi over 4 root 2 minus 3 pi over 4 root 2 is minus 4 pi over 4 root 2. But these 4's can cancel out. And rather than cancelling them out, I'll erase them out so it looks clean. What I really have is a pi minus pi over root 2 times 2 pi, and I want to just present this in a decimal answer, and I'll do that here on the calculator. Pi minus pi divided by 2 root times 2 times pi. I get 5.7815 units cube, representing the volume of that revolutionary solid, or the solid of revolution that I demonstrated earlier. Y equals cosine x between these two intervals rotated on the y-axis, and the question has been done and this answer should be right. Again, just remember our representation was something like this, coming in terms of a cosine from pi over 4 to 3 pi over 4. We had this shaded region right over here and this shaded region right over here, upper part of the x-axis and lower part of the x-axis. Then it was rotated here around the y-axis to demonstrate you can easily do your own graph on the side or your drawing, and you can see a three-dimensional rotational solid will develop as all of these points curve around and then revolve and complete that solid. Thank you for watching. Have a nice day.